All right. So first things first, questions on the homework.
Can we do it to have it handed in on Tuesday?
That's not a valid question yet.
All right. Then can you explain how to start actually?
So question 5, I did not intend to assign, and that uses some stuff that we didn't go over. It's a good one to work through on your own. There's enough information in there to do it, but I'm not going to grade that one.
Okay. Well, how about 3? Can you kind of? I had no idea on NAND gates.
Yeah, 3 is a funky one.
I even tried to like work out the reverse engineer the first one so I could like figure it out, or the solve one.
I found a YouTube video that like totally translated.
How about we just go through all
all
slowly? See, we have to name them out of order.
Well, I found like a Wikipedia thing that basically it's like this is like it showed how to do each gate as a NAND gate. So I was like,
With one man, you mean one.
I have a question.
Yeah.
So for the
Well, that's what I think it's-
NOR gates,
yeah,
the wire, is that like it shorting, or is that just the configuration to where?
So wait, which gate are we talking about?
Well, just
This
like
one or D? So this little circle here is an inversion. Okay, so it's saying this is taking the inverse of D and C, it's ANDing them together, and then it's inverting the output. So let me draw a picture of this, and then we can work on that. So that's an OR, that's an and then those get NANDed.
I guess how would you describe what's happening when it has a square rectangle in front of for the NOR gate?
A square rectangle.
Like the W up there?
Oh, this one.
Yeah.
Oh, it's just W's going into both inputs. It's literally a wire that connects into here. Not really. So here's a useful thing. Suppose you have a NAND gate like this. Okay, this is just a pair of wires, right? It's a 2-input gate, and X is going in here, and it's also going in here. Okay, so you're splitting it off. Inputs you're allowed to split off and have multiple copies of it, right? So you have this in your traffic light. Your southern signal goes one place and it goes another place. These just both happen to be going to the same gate, so it looks a little strange. But what does an AND do? It's a 0 unless both of these are a 1. So a NAND does the opposite. All right, so let's make a truth table for this thing. Let's call this A and B. And let's just make a truth table for this circuit, which has one input and one output. Your input can be a 0 or a 1. Well, if your input is 0, if A is 0, it means that both of your inputs to your NAND gate are 0. That's this case right here. What's the output of your NAND gate? It's a 1. So in this case, B equals 1. But if A is equal to 1, then both inputs of the NAND gate are 1, and in that case, the output is a 0. B is a 0. So this is just an inverter. Takes an input and gives you the opposite value for the output.
Does that work for NOR gates as well?
And that'll work for NOR gates as well. If you write up the truth table, you can convince yourself. Because the only difference between a NAND and NOR is these two rows, and those don't come into play. So this is one way to build an inverter, a NOT gate, using a NAND or a NOR. And that can help you a lot with this circuit over here.
What question are we talking about?
3. Mm-hmm.
So you were saying that, like, I think you said it, that they sent like the Apollo 11
Mhm.
into space with only NOR gates.
Yep.
What's the efficiency of using one type of gate?
Money.
Are other gates more expensive?
Having a set of 5 different types of gates manufactured for you is 5 times more expensive than having somebody make you one type of gate. And there were no commercial NOR gates available at the time. They contracted with a branch of MIT, and a bunch of people there made these physical gates,
Oh, I see.
right?
Okay.
But there's expense and time involved in that, and the more gates you're gonna make, the more expensive, the longer it takes. So someone decided the best overall option is just make a single type of gate, a NOR gate, and we'll come up with a more complicated design that just uses that one gate. Now, how they made that decision, I have no idea. These people who work in the space program are nuts. If you ever look at some of the stuff they do, system level thinking way beyond what I can comprehend. But somewhere they decided this was the best overall solution.
Were these gates like the kinds we use or even bigger?
Were they what?
As big as the ones we use or even bigger?
I don't know if I've seen them physically. That's a good question. I imagine they were, nominally that size, because they were integrated, right? So it was, imprinted silicon with transistors on it. But I don't know what the actual physical dimensions were. You can probably find them online though, because people have archived all of the documentation from there. And I have looked at the original, copies of the original orders for these chips from MIT, but I don't remember what the dimensions were. Mm-hmm.
So what kind of gate was that at CD with the extra circle on the top?
So
of
the
it?
extra circles usually mean inversion. So this is taking D, inverting it, and then ANDing that with C.
And then it's inverted again.
Is there supposed to be an inverter there?
Yeah.
Yeah.
I missed it. Yeah. All right. And then it gets inverted again.
So is that all one chip or is that de-inverted and inverted?
We don't know because this is a logic diagram, not a wiring diagram. It could be one chip, it could be 3 chips, right? This could actually be D goes through a 7404, goes into a 7408, goes through a 7404. Or it could be D, sorry, that's an inverter, goes through a 7404 and then goes into whatever a NAND gate is.
If a D not went through and the other one had nothing attached to it, would that just give us a 1?
If, well, so what are you gonna do on this input?
Nothing.
Can't do nothing. We can ground it, we can leave it high, we can connect it to D. Most of these chips, if you don't connect an input, it acts like there's a 1, but don't rely on that. But if we physically don't connect that pin to anything, it's probably gonna look like a logic 1. In which case, this is probably just going to act like a wire. It's just gonna give you D on the output.
How do you make this circuit without inverters when we're only using NORs when it has to
Because
be
here's a
0,
way
0,
we can
1?
make an inverter, and we didn't do it, but we could. This is another way to make an inverter. So if you NOR something with itself, you get the inverse of that variable.
Okay.
So we can use that to start piecing this together. Up here we need to compute A or B. And since we have a NOR gate, we can do this, and this will give us A NOR B. But we want A or B, we want the inverse of this. Well, let's run it through one of our inverters. Here's A or B.
Will we run that OR gate twice? So we get 2 ARBs?
You could do that, or you could just take this output and feed it into both of those inputs.
But that's only 1, and then you get another 1.
What's only one?
Well, you said we can only, if we don't plug another.
Well, no,
wire to it-
I'm feeding this into both inputs on this 2-input NOR gate.
In parallel?
Yeah, basically,
Okay,
right? So this input's going here, and it's also going here.
gotcha.
So they're not disconnected, they're both getting a signal, they're getting exactly the same signal.
for C or D, you would need to make 2 of those inverters, because you have 2 inversions going on.
At least. But this is a NAND, right? It's not an AND, it's not an OR or NOR, it's an AND. We've got to somehow get from ANDs back to ORs or NORs. And the way we do that is De Morgan's theorem. So De Morgan's theorem tells us that we can do that. And it also tells us that we can do this.
So what does the full bar mean again? Is that the inverse or inverse?
It's the inverse of this expression.
Okay.
So and A and B and then take the complement, or A with B and then take the complement.
Right.
And if we switch from ORs to ANDs, we switch to inverting just the individual terms. That's De Morgan. So there's a number of ways we could implement this block down here. We could say, hey, this is a NAND gate, right? I'm NANDing C with D bar. And so I could get the same thing by ORing A bar with B bar, in this case C bar with D bar bar. So let's do that carefully. So we're trying to generate this. Well, let me get rid of that bubble first, and let me just throw an inverter in. So D is going to go into both inputs of a NOR. So here's my D bar, here's my C, and I want to NAND those. Okay, so De Morgan's theorem tells me if I want to NAND things, I can OR the complement of those two things. So instead of this AND gate, I'm going to take this, complement it. I'm going to take this, complement it. I'm going to OR those together. And that should give me my output right here. Well, I don't have an OR, I have a NOR. But if I complement the output of that, now I've ORed the complement of these two inputs. So this point right here is this point.
So 2 NORs is just an OR?
2 NORs. A NOR with a NOT is an OR. And this is a NOT. This is an inverter. Okay, this is this thing.
Gotcha.
Okay, so it's a NOR followed by, it's another NOR, but it's set up as an inverter. So this is ORing, take the inverse again, that's just an OR. You had yours first.
So, if we wanted to simplify it, could we take out the 2, yeah.
Yep, totally. But if you want to be lazy, don't worry about it. Right. Is that your question?
Yeah.
Okay, cool. All right, so now we've got this, that's right here, and we've got this, that's right here. So these need to get NANDed together. And we know how to do an AND, we just did it. We need to invert this, and then OR them. So one more time, put that through an inverter, put that through an inverter, NOR those, invert the output. There's your final output. And it only took 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 NOR gates. Yeah.
Something we need to like remember.
There's nothing really to memorize here. It's useful to know this, and this gives you an inverter. Okay, but if you remember that there is a way to do that, you can work it out by looking at the truth tables for NORs or NANDs. But this is a useful one to remember. But then it's really just sort of being aware that there is a way to go between ands and ors. And that way is De Morgan's theorem. So we can change ors into ands or ands into ors. And you just have to be careful of the inverse. And then everything that we've just done to go from here to here, right, none of that was memorized. That's really systematically just saying, okay, well, I want an or, but all I have is a nor, so I just have to invert it again. So it's knowing that this is the same as this, right, where this part right here is the nor of A with B, and then we invert it again, because we have a theorem that says not A is A. And this is not something you'd spend a big chunk of your life doing as an engineer, right? It's but it's a useful way to get more familiar with these operations and how ands and ors relate to each other, and being able to look at an OR gate and visualize it as a NAND with inverted inputs. That kind of thing is useful sometimes. So it's not that doing this particular exercise is going to happen a lot, but thinking about what you have to think about to do this is very useful.
The result of that NAND gate at C and D is a 1, correct?
The result of this,
Yeah.
well, let's see what the truth table looks like for that. So when I'm making truth tables, we'll call this X. I don't just start writing down X immediately. I like to do this in pieces. So the first thing I want to do is I want to figure out what's this inverse of D. So let's fill in a column for D bar. And that's just complementing D. And now let's do the AND of these two inputs. So D ANDed with D bar. And that's just this column ANDed with this one. So that's a 0, 0, 1, 0. And then X, which is the complement of C ANDed with D bar. Now I just have to complement this column here. So it looks like that. So it's mostly 1 except when C is 1 and D is 0. And in general, if you have a circuit or an equation and you want to see what the truth table looks like, it's easiest to sort of work in pieces, right? Less work for you to do, and if you get the wrong answer, it's easier for someone to look and see, you know, you got one thing wrong over here, but everything else was fine, as opposed to you just wrote down random numbers because you didn't know what to do. So it's good for partial credit.
Would you be able to go over 7U?
Maybe. 7U is a funny one, and it may have typos in it, which make it even funnier. Funny strange.
I was comparing it to 7S, and it's very different.
Yeah. So we have a demux. It takes in 3 inputs and it generates 8 outputs, right? And so this demux is going to generate zeros on all these lines except 1. And whichever line A, B, and C select, that line's going to be a 1. And they've labeled these M0, M7 to look like min terms. So if A, B, and C are 0, this line up here will be high, all the other lines will be low. If A, B, C are all 1, then line 7 will be high, and all the other lines will be low. Okay, so you got the basic behavior of a demux.
No, sorry.
No,
I was very confused on this one.
Okay, let's draw a demux. So 3 inputs, and they tell us A is the least significant bit,
Or the screen.
C is the most significant bit, and 8 outputs. All right, if we wanted to do a truth table for this, and a truth table is not the most useful way to work with this, but it's useful to help understand what it does. Here's what it would look like. Normally we wouldn't use numbers for variable names, but that's what the problem uses, so. All right, so 8 outputs, 3 inputs. Okay, the way you figure out what this circuit is doing, you look at the 3 inputs in this order, so A is the least significant bit. Suppose your inputs are 0, 0, 0. What number does that correspond to? What integer is 0, 0, 0? That's just 0. So output 0 is going to be 1, and all the other outputs are going to be 0. If your input is 0, 0, 1, that's the integer 1. So output 1 is going to be high, and all the other outputs are going to be low. 0, 1, 0 is 2, so output 2 is high, all the other outputs are low, and so on. All the way down to output 7, inputs 1, 1, 1, which is 7, output 7 is high, all the other outputs are low. So you're choosing one of these 8 lines to set high, and all the other lines are going to stay low.
Why isn't B in our truth table?
That's a B.
Oh, that other thing, yeah.
Sorry. All right, so that's a demux. It's sort of the flip side of a multiplexer. So we can choose one of these lines to drive high based on what value we put into these select inputs, A, B, C. So this circuit is a peculiar circuit because it has OR gates with inverters on the inputs. And an OR gate outputs 1 if any of its inputs are 1, right? Okay, so let me go ahead and copy this. So we have 1, 4, and 7. Those 2 are inverted.
We can see.
No, I'm copying it and then I'll
Oh,
switch
sorry,
over.
sorry.
That's okay, I appreciate it because sometimes I do this for hours and nobody tells me. So 3 and 6. And that gets inverted. That's 1 and 1, 4 and 7.
What are these abbreviations by A and C?
Least significant bit and most significant bit. Have we talked about those?
I've heard about it.
Yeah, like to know that.
Let's touch on that before we use those terms. So you've got a number like this. Don't worry about the number. It's a big number. All right, so this is a 20-bit number. We want to be able to identify the 2 ends of this number, the left side and the right side. Left and right is not a good choice because I happen to write this in this order with 2 to the 0, 2 to the 1, 2 to the 2, so on. But I might have written it in the other order, right? So the way we identify this side is we say this is the least significant bit. LSB. And over here, this is the most significant bit, or the MSB. Okay, in what sense is this least significant? This is some number. This is a number like, let's see, 20 bits. So this is like, you know, approximately 1 million. If I were to change this bit from a 0 to a 1, is my number going to change a lot in value? It's going to change by 1. It's going to go from 1,500,000 something to 1,500,000 something thousand and 1, right? So not a very significant change. But this bit over here, if I were to change that to a 0, my number is going to go from around 1 million to around 500,000. Or if it was a 0 and I change it to a 1, it would go from around 500,000 up to 1 million. It's a very significant change, right? Because this is the 2 to the 19th position, this is the 2 to the 0th position. So this is called the most significant bit. It's the bit that has the biggest impact on the value of the number. So we use that to designate left and right. And almost always we'll write numbers like this with the most significant bit on the left, least significant on the right. But when you're working in code where these things aren't written on paper and there's no natural notion of left and right, we still need a way to refer to these two ends. So you'll use LSB, MSB. So that's what that abbreviation is all about.
What about decimal?
Like real numbers? We can still use LSB, MSB to refer to parts of that, but we're going to take another class where we actually talk about how we represent decimals in binary. So it's something called IEEE 754, a floating point notation. But when we discuss that, we'll still use the language of least significant bit, most significant bit for the pieces. All right, so this is a weird circuit, okay? But let's think about what this does. Suppose we make a truth table. And we just list all the possibilities. All right, suppose our inputs are 0, 0, 0. We just said this line is going to output a 1. All the other lines are going to output zeros. So what is F2? It's a NOR of line 1 inverted, line 4, and line 7 inverted.
Why is it a NOR?
Because it's got this half moon shape to it. It's an OR.
Oh, or, I thought you
Yeah.
said.
Oh no, it's a OR as opposed to an AND.
Oh, sorry, I misheard.
Okay, my bad. So what is line 1 in this case, where A, B, C are all zeros? What's the value on line 1? It's a 0, right? And that 0 gets inverted, so we have a 1 going into an OR gate, and we can stop right there. This output's going to be 1.
Why is that a 1?
Because this is a 0, because this demux outputs a 0 on every line except line 0. So this line is low, and this bubble says we're inverting that input. So 0 inverted is a 1 going into this OR gate, and a 1 ORed with anything else is going to give us a 1. So F2 is going to be a 1. In the second case, where our input is 0, 0, 1, we know that line 1 is going to be high, so this line here will be a 1, and all the other lines will be 0. All right, well this is a 1, gets inverted to a 0, so we have a 0 going into this OR gate. So far the output is 0. But down here at line 4, this is a 0, goes into an OR gate. We've got another 0 in the OR gate. The output's still 0. But line 7 is also low. That gets inverted to a 1, 1 going into an OR gate. That's going to be a 1. And so you do this kind of analysis for all 3 outputs, for all 8 possible combinations. But as you do this, you'll start to see what's happening, and it's going to become really quick to fill in the whole table once you get through a few rows for each output. But that's the process. The other thing on here, there's this input labeled EN, and there's a circle here, and there's a line, and this is not an arrow, it's a ground symbol, I'm going to assume. A lot of these chips have what are called enable inputs. It's a way to basically tell the chip whether it should be active or not. And if we don't enable this, then presumably all these outputs will be low regardless of what A, B, and C are. So to make this chip actually do what we said it does, the enable input has to be high. But there's a bubble in the beginning, which means that we need to put a 0 into this bubble, which will invert it into a 1, which will go into the enable input, which will enable the chip. So the terminology we hear sometimes is active low. Okay, this is an active low enable input. When you want it to be active, meaning enabled, you have to put in a 0 instead of a 1. And a more common way of describing that would be to write it as EN with a bar on top. And then we think of this as the complement of the enable input. So a 0 would enable it and a 1 would not enable it. But it's the same thing as writing a bubble in the beginning. These are just things that you'll see in data sheets as you go through engineering. There's lots of different ways to represent different things. And there's some standardization, but there's some things that aren't. Just like when we have a gate with a bubble on an input, right? We could simply draw an inverter right here and then just go into a plain old-fashioned OR gate. But it's a common notation to just draw a circle here and understand that that means there's an inverter. And there's tricks you can learn to deal with these bubbles and push them through to outputs. And it's a technique literally called pushing bubbles. But we don't need to go there. We can always think of it as just being an inverter, and we can use what we know about logic gates and inverters to analyze these. Yeah?
Did we talk about 5 yet?
5, we can talk about it. So 5, I said I'm not going to grade because I didn't mean to assign it.
Oh. 7. Just want to know what the W's mean.
It's something that I am going to talk about.
It's not yet.
I was going to talk about it today, actually. It's called compressing a truth table. So let me get to that in lecture.
Okay.
But don't worry about doing 5. But we'll go over it in a bit. Yeah.
I'm sorry to ask you this, but can you do one more example on 7? I'm still a little lost on the truth table.
Okay. You do not have to apologize. So, should we do a different output?
Yeah.
Let's look at F0. So F0 is, this is where it's unfortunate. Let me call these like X0, X1. So F0 is X0 ORed with X4 bar ORed with X7. You see that? Okay. And depending on the value of A, B, and C, exactly one of these X's is going to be 1, and all the other X's are going to be 0. That's what the demux is doing. So if A, B, and C are all 0, X0 is going to be 1, X1 through 7 are going to be 0. Right? So this line will be high, and everything else will be a 0. Well, if this line is high, we've got a 1 going into our OR gate, right? As soon as we know X1 is a 1, we know that the OR of that with these is going to be 1. Yeah?
is there an instance on one of these where it says 0?
I don't think so.
Okay, because I
Yeah.
was thinking, okay, so they're all 1.
Yeah.
Well, there is one this one, wasn't it?
Is there one?
When it-
Oh yeah, for F1.
Yeah. Well, and F0.
And F0, yeah, there'll be one, which is when,
I did F2. not all.
okay, F2 will be all ones.
Okay. That's
Um,
what I did.
But let's take F0 up to an entry of 4. So if our entry is 0, 0, 1, right? So A is a 1. So we're looking at this. So X1 is going to be 1. So this line is high, and these other lines are low. Well, we've got a 0, a 0, and a 0. 0 gets inverted to a 1, right? If X4 is 0, this is going to be 0 or 1 or 0. That's going to be a 1. And if our input is 0, 1, 0, X2 is going to be high. Well, X2 doesn't come into this gate, right? So this is exactly the same as the previous case. And in case 3, where X3 is high, again, that doesn't affect the output F0. But let's look at this case here, 1, 0, 0. So here, X4 is high, so I'll put it in red. This is a 1. So we have a 1 here, and all the other x's are 0, so this is a 0 and a 0. And if x0 is 0 and x4 is 1 and x7 is 0, right, that 1 gets inverted. This is 0 or 0 or 0. That's going to have an output of 0. But then all the other cases are going to look like those first few cases. It's going to turn out to be 1.
So how's X0, X7, 0? Or 1?
So this is 0 or 1 bar or 0.
Where do you get the 0 from?
This one?
Yeah.
Because if your input is 1, 0, 0, this is what the demux is outputting. So x0 is 0, x4 is 1, x7 is 0.
Oh, okay, so you look for on that one.
Yeah.
So for my answer, I wrote F1 equals the sum of midterm not 3 and midterm 6. Is that something what you're looking for? Is that a correct answer?
I'd rather see a truth table.
Because if
Well, it says analyze the following design. So, so what does that mean? So I wouldn't put that on a test. I would be very explicit. I'd say write a truth table or write equations. If you write equations with your min-terms, right, that's a first level analysis. So that would be at least a step in the right direction. But if I did this, I would probably say write a truth table,
okay.
right? So then you'd want to go from there to actually filling in something like this. But it didn't really specify in there, so which is another reason I don't create that problem. Yeah.
So what are you looking for when we do this one, number 7?
I'm looking for a lot of effort. And like I say, I wouldn't grade that one. If I was going to grade that one, I would be sure to specify. Make sure for number 7 you do a truth table, or for number 7 do equations or something like that. So the goal here is primarily to work with a demux, right, and start to develop this feel for, yeah, there's a truth table for it, but really what this is doing, it's choosing one line to assert. Okay, assert meaning drive to a logic 1. Exactly one of these outputs will be asserted based on what's selected by those inputs.
Is there like a quick purpose you could use as an example of a demux?
Yes, so the previous version of this is a little bit more interesting of a circuit. They've got inverters on all the outputs, so this is actually just a plain old OR gate of min-terms 1, 4, and 7. So this is going to be 1 when either min-term 1, min-term 4, or min-term 7 is asserted, which means if your input is 0, 0, 1, 1, 0, 0, or 1, 1, 1, F2 is going to be 1. So F2 is this sum of these 3 products, and we can code that with a demux and an OR gate. And F0 is going to be 0 when your input matches minterm 0, minterm 4, or minterm 7. But this one got a little pathological because I think it works better if you have bubbles on the outputs, or you get rid of these bubbles. Yeah.
So for the example on the 7S, the
Mhm.
solutions have the, like, an equation with summation.
Mm-hmm.
How would we write that for the one for 7U, for like F2? Like, would we just have,
So F2 is, let's see. So F0 you said, or F2?
F2?
F2 equals, just say F2 equals 1.
Oh,
Right, that's still a Boolean equation. It's just a really kind of minimalist one. And this would be M4 bar. Right, if we said F0 equals M4, that would be 0 everywhere except in row 4. So if we write M4 bar, we get that, or we could write F0 bar equals M4, which is what they did in the solved version. Mm-hmm.
can you introduce problem 8?
8's a fun one. Did you look at the solved version at all? So when we talked about multiplexers, we said something about how we can use them to generate random logic. Right, so if we have a function we want to generate, and rather than fill in specific ones and zeros, let me just call these things A, B, C, and D, where those are ones and zeros, right? If I were to connect these inputs to either 5 volts or ground, 5 volts if that's a 1, ground if it's a 0, and then take A and feed it into here, and B and feed it into here, this generates that truth table. Okay, why? Because if A and B are 0, this demultiplexer selects input 0 and passes it to X. So X is equal to whatever value is coming in here, which is A. And if A, B are 0, 1, then this says take input 1 and send that to X, and input 1's value is whatever I connected it to, whatever the value of B is, and that's what X is going to be. So we can take a truth table and implement it with a demultiplexer by just feeding the inputs, the values from the truth table, and feeding the inputs to our circuit into the select lines. And that's what's going on in question 8. They have a mux, not a demux. They have a mux and 2 select lines set to A and B, and they're just hardwiring the values of D0, D1, D2, and D3. D3 is connected to 5 volts, so that's a logic 1. D2 is connected to ground, that's a logic 0. D1 is connected to some signal called A1. We don't know what its value is, but we don't need to. And D0 is connected to another signal, A0. And so if S1, S0 are 0, 0, our output's going to be D0, which is just A0. Mm-hmm.
How can you tell what's connected there?
Connected where?
On the left here, all the lines are just crossing each other.
Oh, if two things don't cross, if they meet in a T, there's a connection. And if there's a dot, there's a connection. Otherwise, they're just crossing.
Crap.
So there's a connection, there's no connection.
Gotcha.
And usually there's dots all over the place, but I usually draw a heavy dot regardless. All right, so 0, 0, the output will be A0, 0, 1, the output will be A1. What would the output be if your inputs are 1, 0? Yeah, so if it's inputting from D2, the output would be 0, because D2 is connected to ground. And if it's 1, 1, it would be D3, which is a logic 1. So it's a way to design, to implement truth tables using multiplexers.
So for the answer to this, would it be better to write out the entire truth table with like the ranging values of A, B, and A naught and A1? Or would it be better to just say that whenever it's like D0 or D1, then it's just A naught or A1?
So this they made a little tricky because they want you to write this as a function of 4 variables, AB, A0, and A1. So imagine a truth table with 4 inputs, AB, which are going into your mux, but also A0, A1, which could be 0, 0, 0, 1, 1, 0, or 1, 1. And for each of those, write down what the function f is. So your truth table answer would be 16 rows, and it would show you explicitly each possibility for A0 and A1. And then it asks you to write your answer in compact minterm form, so that's just the sum of M0, M2, M3, that kind of thing.
I mean, that's what I did. I wrote up the 16.
Okay, cool.
I wasn't sure if that was like...
Yeah, that's what they want. All right, so here's your deal. If you want to turn your homework in right now, I will grade it. I will give you 5 bonus points for turning it in right now. If you want to keep it and turn it in on Tuesday, I'll grade it as usual without the 5 bonus points. You're probably not going to lose more than 5 points unless you didn't do your homework at all, though. So it's probably worthwhile turning it in today. But it's up to you.
Can we return it in for more points?
No.
What questions was it all again? 1, 3, 5, 7, and 8?
Something like that. 2 might have been in there also. 1, 2, 3. Did it do 2?
I don't think we did 2. Oh, I guess we did do 2.
Okay, so 2's in there also. And then 7 and 8. Yeah. What's the last tab?
Oh, yeah, 10 and 11.
Those 10 and 11? No, those I said hold off on
Those got removed off though.
because we didn't get through all the programmable logic. We're going to do that this afternoon. All right, any other homeworks? So really quickly, any lab 4 questions so far? That's the lab you're doing now. Cool, thank you. So your lab 3 is graded and turned back to you if you turned it in on time. If it came in late, I'm holding off a couple of days to grade. I'll grade it this weekend. But lab 3's looked good. Everybody got the truth table correct for experiment 2, which has never happened before. So That was nice for lab 3. So experiment 1, right, all 3 light bulbs light up. You should have observed that configuration 3 is a little dimmer than the others, right? Or maybe configuration 2, but there is a difference in brightness. But they should all light up, and I think that's what everybody got. And it's just 3 different ways to drive an LED, right? Here we've got 5 volts going through the LED to ground, currents flowing from left to right, that lights the LED. Here, instead of hooking up to 5 volts, we've got the output of an inverter, but the input's 0. The output is logic 1, that's about 5 volts. 5 volts to ground, current flows left to right, LED lights up. In the third case, the inverter's input is high, so the output is low. So this point here is basically ground. 5 volts over here, ground here, current flows from right to left. That's the forward direction of the LED. LED lights up.
What would happen if the inverter wasn't there?
This one,
Yeah.
you'd have 5 volts and 5 volts, there'd be no current flow. So the LED would be dark.
Just be like,
Yeah, but it doesn't actually, kind of does, but it's more just there's no difference in potential,
okay.
right? So if you think of the water pressure model, if you have a high pressure tank that's up here and a low pressure tank here, water will flow from high to low. If they're both at the same level, you connect them with a pipe, there's no flow from one to the other because the pressure is the same on both sides.
Gotcha.
All right, so this one, right? Everybody got the truth table. It's amazing. So I don't have to talk about that, right? It just does what it does. And then experiment 3. So most people did exactly what I asked you to do, which was also awesome and rare. So intersection and truth table. Most of the truth tables had 6 outputs, which is good, and then sum of products and product of sums, unsimplified, right? So big long expressions, and then drawing circuit diagrams for those, and usually it was 2 or 3 pages of very tiny gates connected together. And then so far everybody has chosen to use the sum of products, so that needs to get minimized, write down the equations, and then do a wiring diagram for that. And a few people didn't actually do a wiring diagram, but everybody who did looked like the diagrams were right, including the switches, which is like very cool. I want all you in my 270 class because I won't have to teach you how to do switches again. So yeah, so that looked good, and also lots of cool new experiments. New experiments, a few cases where there still weren't details given to tell somebody what to do. Okay, so you got to have details in there. Typically, the new experiments are at least a couple of paragraphs describing it. And if you're putting in expected results, some people are spending a whole page on the new experiment part, right? And it kind of makes sense. I mean, look at experiment 1, right? It starts here and it goes down to here. Experiment 2 starts here, goes down to there, right? Experiment 3 is half a page, but it's a very dense half page. And it's extending on 2 or 3 other previous experiments. So don't spare the details in there. All right, let's take a break. Come back and we'll finish talking about chapter 3 stuff. And we'll end on some weird philosophy.